Okay, so I'm going to, I don't hear anyone yelling at me, so I'm assuming everyone's signed in. So today we're going to be talking about what we're calling breakdown of an experiment, but really it's sort of like an introduction to thinking statistically about an experiment or like a research project, things like that. And I'm going to start off by saying that this is not a lecture that I normally give. Usually someone else gives it, but I was second in line because people who've done it in the past are out of town, and a person has moved to another university. So I've heavily modified the slides I was given. I still think that this might be like three-hour workshops worth of material. So I think there's a decent chance we're not going to make it all through. I already cut some stuff, a lot of stuff, but you still might not make it through, or maybe I'll surprise us all and we'll finish in an hour and a half. We'll see. But please feel free. So I'm going to try and go quickish, but please feel free to, I'd rather not get through everything and have people understand rather than rush through everything and lose half of you. So please feel free to interrupt. If you're on Zoom, you can unmute and say something. You can try and put something in the chat, but I might miss it. So if you put something in the chat and then I'll respond in a couple of minutes, then please yell or unmute or put it in the chat again, something. What else do I want to say? I think that's it for now. Okay, and actually, sorry, the other thing is that I'm going to mostly be working from, or I'm potentially only going to be working from slides here, but there's a little bit of code here. I mean, the focus here is more, you've already covered a lot of R, and so the focus here is not necessarily doing things in R. There are like several times where I'm gonna do things in R, but the focus is really in sort of more conceptual. So I'm planning on working from slides, but if people have questions about chunks of code that I'm gonna show, I can open up RStudio and we can work through them. Okay, so you already saw the sign-in sheet, and so did anyone not sign in? Okay, great, thank you. So here's the learning objectives and goals. We're gonna talk very generally, sort of philosophy of science, about the scientific process. We're going to talk about different ways to sort of statistical approaches to summarizing data, and we'll talk some about why do we need statistics, things like that. So we'll talk about numerical summaries and then graphical summaries of data. And so we're working with, I'm going to be giving examples from 2 different example data sets. So I'm just going to introduce you to those quickly. The first one, which I'll just be calling case study number 1, because I'm not going to remember the title. So this is the title of the publication, is Efficacy Trial of a DNA Rad5 HIV-1 Preventative Vaccine. And here are the links. Oh, I should say that I haven't put the notes from today up on GitLab, but I will. I need to do a little bit of GitLab magic because I branch things and stuff like that. But I will, so you'll have these links. So there's the link to the original article from the New England Journal of Medicine. The data itself is available through SHARP, which I cannot remember what it stands for, but it's a repository for, I believe, just HIV vaccine research. And that's the part of the link. It'll work in the notes, but it's cut off there. And so we'll just take like a little bit of a quick tour through the data. So, so for case study one, whoops, I just see something that I think I forgot to update. So for case study one, this is the data dictionary, and it's actually provided, SHARP has it as I think an Excel spreadsheet. So the code that's underlying these slides just parses that Excel spreadsheet. And here we're looking at just part of the data dictionary. I think I have 2 more slides showing it because there's like 20-something columns. And so you can see there's, you know, things that aren't necessarily very interesting, like a publication ID, things like that. But there's information on the treatment arm and things like that. Something cut off. Looking at, you know, like whether they got the second dose of the vaccine, the first dose of the vaccine, the third dose of the vaccine, different stuff like that. Body mass index, race, gender, other things. Seems like there's, oh no, never mind. Okay, so that's the data dictionary, and here's just like a peek at just the top 6 rows in the data set. And you can see that the like column names don't necessarily make much sense. That's what the data dictionary is for. If you look at the second column, the data dictionary, the variable name, that's where you get the explanation for these values. And then the second case study is called a superior, and I'll call this case study 2, that we'll be using data from. So a superiority of viral load over CD4 cell count when predicting mortality in HIV patients on therapy. And there's the link to the article. And I'm going to explain, as we sort of like over the next few minutes, sort of talk about how to think about designing a study, or like how studies are designed, how to think about them statistically. I'm going to give you some details about like what different questions that went into the design of these studies, but just wanted to like give you a quick intro to the data. So here's the data dictionary for case study 2. It wasn't, it's not provided in a sort of simple parsable format. So this is just manually abstracted from the paper. And so you can see that there are things of like age of the subjects, gender, weight, the HIV, RNA, viral copies in bloodstream, things like that. And then here's just, again, a snapshot of the data. We're actually going to be looking at, just to make things a little bit more simple, this is a study where measurements were made on the same subject. It's a longitudinal study. We'll talk more about that in a second, or in a few minutes. But it's a study where measurements were made of the individuals over an extended period of time. For this data that we're looking at, and for like the examples that we're going to be working with for case study 2 data, we're just looking at the baseline data, which means time 0. So the time at which the subjects were, for each subject, the time at which they were enrolled in the study. Okay, any questions about that before I go on? I know there might be questions about like what's actually like the scientific question, but like I said, we're going to get to them. Oh, actually, one more thing that I wanted to say. is that I'm planning on trying to take a break right around 2 and another break right around 3, because I know that especially on Zoom, it's people get like, at least I get like fuzzy after probably less time than that. So we'll take like maybe like a 10 or 15-minute break around 2 and around 3. Okay. So let's talk about think about the scientific process. And again, this is somewhat like philosophical, but it's helpful in thinking about how do we plan a study, how do we think about how we're going to analyze the study. So this is potential steps in the scientific process. The first step here is an observation or a pattern. The second step is based on that formulating a research question. The third step is based on the observation and pattern and the research question, developing a research hypothesis. And then based on the research hypothesis comes the study design and the data collection plan and data collection. And then there's a statistical analysis of that data. And then one draws conclusions based on the results of that analysis. So there are several caveats to this. Number one is that how I'm phrasing things here, and a lot of what I'm going to be talking about for the rest of today, it's biased towards clinical research. So that does not mean, and I'm sure many people here know that doesn't mean that all research has to be clinical research. Not all research even has to have anything to do with humans. But because of the sort of theme of the workshop, we're going to kind of bias things that way. Another caveat is that if you look around, people will phrase these steps differently and sometimes order them differently. And then the third huge caveat is that this is sort of a theoretical way of thinking about science, but often if you we're an anthropologist watching scientists, you might see that the process isn't really linear like this. You might actually start with like some sort of hypothesis and then like go back to an observation and, or have like a research question. So the order isn't always so linear and straightforward like this. It really is going to depend on the science that's being done. It's going to depend on the field. And so this is, again, sort of a theoretical, philosophical way of simplifying things, but the real world tends to be messier. Okay, so we're going to walk through each of these steps for the 2 different case studies. And so for case study 1, our observation or pattern is that there's no effective vaccine for HIV. For case study 2, the observation or pattern is that people living with HIV have diverse health outcomes. And I'm going to say again that things aren't necessarily so simple. So I actually, looking at these studies, I've framed a lot of the observation pattern and some other steps differently than other people might have framed it. So this is the way that I'm framing it. It's not necessarily exactly the way the people who did the research would have framed it. But again, so things can be messy. But this is the way that I'm thinking of framing the observation for these 2 case studies. So the research question, so I'm repeating the observation here just for context. So the research question for case study 1 is, so first of all, there's there's a little bit of more information that's kind of, to some extent, a little bit of hypothesis. Or I guess it's not more detailed observation. So with a little bit of hypothesis in there. So again, the initial observation is there's no effective vaccine for HIV. Like a somewhat more detailed observation is that the genetic diversity of the HIV virus circulating in humans may contribute to the challenge of developing an effective vaccine for HIV. I suspect that probably everyone knows that people have been trying to develop, scientists have been trying to develop HIV vaccines for 30 years, 40 years. And so far, there's been one vaccine that had some benefit, but not a lot. So vaccines have gotten more complicated, more sophisticated. Our understanding about why vaccines don't work or why different vaccines that have been tried haven't been effective have gone into this second observation. So based on this observation, we have a research question, which is, would a multi-gene, multi-clade DNA prime recombinant adenovirus type 5 vector boost vaccine be effective? Again, be effective as a vaccine. So for case study 2, again, our observation was people living with HIV have diverse health outcomes. And our research question is there a difference in HIV control between those who adhere to their medications and those who do not? So moving on to the research hypothesis, first let's before we get into a research hypothesis for each of the case studies, we'll discuss a few ground rules. So in the simplest form, so a research hypothesis, it's a statement about what the results are, what sort of results might be expected. And the goal of the hypothesis is to try and answer the research question. And so if you want to formally state a research hypothesis, you have to state it in a way that's testable. So for example, if you say, I hypothesize that the sun orbits around the Earth, you need to be able to generate some data to support that hypothesis. I'm not saying that that's my own hypothesis. I'm just saying that that's a hypothesis. So if the research hypothesis isn't really testable, then it can still be a hypothesis, but its utility in sort of planning out research is limited. And so generally, if you want to have a testable research hypothesis, you want to state it in terms of the primary outcome of the research. So like, what outcome do you expect based on your previous observations, other information? And so the primary outcome has usually will have specific characteristics that make it so that you can actually try and answer the research question. So again, it needs to be measurable. So it's something that you can measure or compute for every individual. Here I say individual, but again, that's sort of clinical research focused, right? It can be, if I'm studying buildings, then the individuals would be buildings, or if I'm studying, apples, then the individuals would be apples. But you need to be able to measure whatever value you're interested in for every individual, every unit in the study. So here, again, clinically biased, but I'm saying that the primary outcome should be clinically meaningful. But we can, rephrase that for, it doesn't have to be like clinically meaningful, but it should be meaningful for, say, apples. It doesn't need to be clinically meaningful, but it should be meaningful for, how sweet is the apple? And then the other key characteristic of the primary outcome is that it should be the result that's of greatest importance, right? So you can measure other things and you can have secondary outcomes, but really it should be relative to the research question. You should try and, the goal should be to pick a primary outcome that will, that's the most interesting, the most important. And then from a statistical perspective, the hypothesis will normally have two components, the null hypothesis and the alternative hypothesis. So the alternative hypothesis is, the null hypothesis is what you are, the alternative hypothesis is really like, if I think that Granny Smith apples are sweeter than Red Delicious apples, that's my hypothesis based on previous observations, where I say that Granny Smith apples are sweeter than Red Delicious, right? So that's would be the alternative hypothesis. The null hypothesis is that I can't identify any, there's no statistical difference in terms of sweetness between the two apples. Okay, so let's think about research hypothesis for case study one. Again, I'm repeating the observation and the research questions here. So our primary outcome, or the primary outcome from the study, is vaccine efficacy. And so before we go into details about that, I'm going to take a little bit of a detour and talk about what efficacy means. So efficacy means it's a measure of whether the treatment decreases the risk of a potential outcome. You can also flip it on its head, depending on what the goal of the outcome is. So like here in this case, well, actually, I don't want to step on my punchline, but you can flip that on its head, and you could say like, well, actually, I want for this treatment, my goal should be to increase the risk of a potential outcome, or the likelihood of a potential outcome. It depends on what the treatment is and what the research question is. But basically, the question, efficacy is a measure of how likely the treatment is to, or how effectively the treatment is going to increase, decrease outcomes of interest. And it's important to think about the fact that that how one defines efficacy is really very dependent on what you're studying. And so really, it's going to be pretty domain specific, and it's sort of up to the people doing the research, planning the study, to determine what a reasonable measure of efficacy is. Okay, so for case study one, actually, I want to have, I'm going to give everyone like a minute to think about this. So I said that the primary outcome here is vaccine efficacy. Take a minute and think about how maybe we could rephrase how we could phrase vaccine efficacy as a primary outcome as a research hypothesis. And then I'll share what I came up with. So your usually you have an alternative hypothesis, and then the null hypothesis is, the null hypothesis is basically that the alternative hypothesis is wrong, I think is one way of thinking about it. So I gave the example with the apples, right? My research hypothesis would be that Granny Smith apples are sweeter than Red Delicious apples. And then the null hypothesis would be that I don't have any evidence to support the fact that, support the hypothesis that the alternative hypothesis. And so actually, since you asked, I'll just clarify that if for that example, people often actually get confused about this. So for that example, that alternative hypothesis is that Granny Smith apples are sweeter than Red Delicious apples. If the alternative hypothesis, if I don't prove the alternative hypothesis, that doesn't mean that I've proved that they're equally sweet, and it doesn't mean that I've proved that Red Delicious apples are sweeter. I've only failed to prove that that Granny Smith apples are sweeter, right? And so there's actually, if you want to prove that they're equal, that's actually a different kind of statistical measure. And if you want to prove that the other one is sweeter, then that's also, you could, yeah. But failing to prove that something is true doesn't mean that you prove that, failing to prove that one is greater than the other does not mean that you've proved that they're equal. So no brave people want to suggest a research hypothesis? Maybe this is too much of an ask. Okay, so I'll tell you what I came up with. The primary outcome that I came up with is that vaccine efficacy in decreasing the risk of HIV infection, right? That the vaccine is efficacious in decreasing the risk of HIV infection. And then based on that, what should the research hypothesis be? That the vaccine will decrease and this is how I'm phrasing it, that the vaccine will decrease the risk of HIV infection in comparison to the placebo, right? So that's my alternative hypothesis, that the vaccine will decrease the risk of that outcome of the HIV infection, that's the outcome, in comparison to the placebo. So then in this case, the null hypothesis would be that the vaccine does not improve upon, does not decrease the risk of infection in comparison to placebo. Should we try again with case study number 2? Okay, so remember that the observation and the research question the observation is that people living with HIV have diverse health outcomes. And the research question is there a difference in HIV control between those who adhere to their medication and those who do not? I think that I might have some definitions here. So, no, maybe not. So what should the primary outcome be? I think we actually have definitions coming up. So think about it remember that it should be something that's measurable. Okay, so viral load, that's that could be a primary outcome. So medication adherence is a possibility, but this gets into sort of complicated, tricky territory. So medication adherence is a possibility, but the way that I've phrased it, it's worth thinking that medication adherence is going to, at least it sounds to me, and I guess I thought about this, that the medication adherence is actually going to be an effect on something else. And so that might not be our primary outcome. I've got someone in the chat said HIV control. So we have viral load, we have HIV control. And so, yeah, so the way I phrased it here was HIV control, but specifically, how are we measuring HIV control? So one way to measure it is in terms of viral load. And so in this case, we could choose, if we want to keep things simple, there are different ways we could do this, but if we want to keep things simple, we could basically have a binary, something that we can answer with a yes, no, right? So in this case, the way that, and again, I'm not expecting people to know this off the top of their heads or like people without HIV experience to necessarily know this, but the way that I've phrased it coming from the paper is undetectable viral load, which basically means less than 50 copies per mil of viral RNA and less than 50 copies of viral RNA per mil of blood, right? So either the viral load is undetectable or it is detectable, right? So meaning that it's greater than or equal to 50 copies of viral RNA per mil. Okay. So that's our primary outcome. So what research hypothesis, or what are some research hypotheses that we can come up with? And I'll give you another minute on that. You can write it out or, just have it in your head. Okay. Anyone want to suggest a research hypothesis?
Right. The group with greater medication adherence will have a greater proportion of patients with undetectable viral loads after 28 weeks.
Okay. Yeah. Good. So I'm gonna actually, I should tell the people in the room. So if you yeah, sorry. You want to say it again?
Yeah. Sure.
Okay. Yeah.
Greater medication, the group with greater medication adherence will have a higher proportion of patients with undetectable viral loads at a certain week number.
Okay, great. Did people on Zoom hear that? Okay, great. Okay, and then I got another Zoom answer. Although it scrolled off the screen and I lost it. So I see part of it. I think it was people adhering to medications will have a lower viral load than people who don't, maybe. And I'm sorry if you said something else because unfortunately I can't see much of the Zoom chat and I don't think I have a way of controlling it. Okay, so here's what I had, which I think is similar to that. Come on. There. So the way I phrased it is similar. So there's a difference in undetectable viral load between those who adhere to their medications and those who do not. And actually, now that I look at that, I think I might actually phrase it differently. I might phrase it that I think more like the way that other people phrased it, that people who adhere to their medications would have, would be more likely to have undetectable viral loads. Because mine's a little bit wishy-washy there. Okay. So now, so we talked about observation, research questions, research hypothesis. So let's talk about study design and data collection. And I will say that I took out a lot of details in the interest of time. And I can't remember if I totally deleted them or if I think I stuck them at the end. If we get to them, we can talk about them if I stuck them at the end. Okay, so again, we need to sort of think a little bit about sort of philosophy. And we need to think about the difference between a population and a sample. So there's a sort of driving principle in statistics that we want to describe and make predictions about a population based on measurements of a sample, and population and sample are like technical or specific terms in statistics. And so a sample is a representative subset of the population. So what's a population? So it's all the individuals, or again, for a technical term, sampling unit that meets some criteria. And again, when I say individuals, like you can think of that as human beings, but it doesn't have to be human beings. It can be bacterial cells, or it can be, you know, cartons of ice cream, or it can be cars, or it can be planets. So whatever it is, the sort of unit at which you're measuring things. So just an example of different populations. And again, this is population here is a technical term. So it's, you know, slightly different meaning than how we use it in everyday speech. So one population could be all people with new HIV infections in the year 2020 worldwide. So another population could be all the people with new HIV infections in the year 2020 in the United States. Another population could be all the people with new HIV infections in the year 2020 in North Carolina. And then another population could be all the people with new HIV infections in 2020 in the city of Durham. Right, so those are all different populations. So obviously, like all the people in the population that's the people with new HIV infections in 2020 in Durham City is going to be a subset of the population of the people with new HIV infections in 2020 worldwide, right? But those are all populations. So I don't have, when I say population, I don't necessarily, just be clear, I don't necessarily mean like all the people in the United States or all the people in North Carolina, right? I'm defining certain characteristics that I'm using to define the population. So we can also define a population as all the people within 1 hour drive of a Duke hospital, or all the homes within Durham County, right? Again, we're not necessarily talking about people, or it could be all the pine trees in Duke Forest. Questions about that definition? Okay. So why should we bother to sample? Why not just measure all the individuals in the population? So it's usually, it's often impractical and sometimes impossible to measure all the sampling units in a population. And the reasons for that, there's several different reasons for that. It can be just cost, right? If I want to sample all the people with new HIV infections in Durham City, like that might be feasible to do, but that might be very costly to do. It can also just be difficult identifying the sampling units, right? So like current example is all the people who will vote in an upcoming election. Well, how do you identify all the people who are going to vote in the upcoming election? You know, even if you could, like, you know, you ask people and they tell you and their answers are accurate, which, you know, you don't know, like someone could say like, oh yeah, I'm definitely going to vote. And then, you know, they're sick that day, or they're in a car accident, or someone in the family dies and they, you know, they go to the funeral or something like that, right? So there are all sorts of reasons why it can be difficult to identify the sampling units. And just to take that example a little bit further, right? Even if you could directly ask people and get the answer, you have to be able to contact all the people. And like, I know that like, I get phone calls that I ignore, right? So people are trying to contact me sometimes to ask me questions and I might be ignored. And then another reason why to sample is just, you know, that because it can be difficult or impossible to measure all the sampling units in a population, can be the laws of physics. So like, let's say my population is all the babies born at Duke Hospital between 2020 and 2030. So I want to know that now so that I can make, you know, sort of plan how many, I don't know, how many beds I'm going to have in the you know, labor and delivery, or how many pediatricians I want to hire, things like that, right? But it's 2024 and I want to know how, like, I want to know something about all the babies that are going to be born this decade. So I don't know how many babies, or I don't know anything about the babies for sure. I can't measure those babies that are going to be born next year, the year after, the year after, the year after that, right? So the population might not be accessible because of the laws of physics, because I can't travel to the future, right? So there are all sorts of reasons, again, for sampling. And like cost is, again, a pretty common one, but it's often much more sophisticated than that, or much more complicated. Questions about samples and populations? Is that clear, right? What the sort of statistically, what the difference is between a population and sample? Okay, so let me talk about a few different like study descriptions and classifications. So 4 major things I want to talk about, and then I'm going to get into details of each of them. One is the control over the study environment. 2 is the timing of the study. 3 is the measurement, the timing and or spacing of measurements. And then the last one is blinding. And again, this is somewhat biased. Aspects of this are sort of specific to clinical research, but not all of them. Okay, so the concept of control over study environment, we can sort of throw studies into 2 major groups. One is an experimental study and one is an observational study. So in an experimental study, the research is intentionally manipulating the environment, and here I'm using the environment not to describe like the world outside the building, but to describe the ecosystem of the world of the study. So in an experimental study, the research itself is going to manipulate the environment. It's going to have some effect on subjects in the study. So that can be, you know, giving some people in the study a medicine, or giving them some sort of training, or, you know, asking them to do something or ask them not to do something. And so, or like other examples here could be like giving, you know, maybe those individuals are taking some medication. You ask them some of them to take twice as much medication or half as much medication. And then usually the goal of some experimental study is to see how that manipulation of influences the primary outcome, right? So that's an experimental study. You're actually doing an experiment. An observational study is you're just watching. So you're collecting data. So I have here the phrase sit back and watch, right? So you're collecting data and trying to make inferences based on the data that you've collected, but you're not, it's purely observational. You're not actually impinging on the environment, right? So, like key difference, whether you're whether it's an active or a passive research project. Okay, so here's brief descriptions from case study 1 and case study 2. I don't know if I even need this information to give you this information or not, but thoughts, I'll give people a second to read, actually. Read case study 1 and, or this little snippet from case study 1. And then the question I want you to think about is, do you think that this is an experimental study or an observational study? And then read the snippet for case study 2 and the same question. And I'll give everyone a minute to read this. Okay. So, anyone want to, or maybe I'll do it this way. Who thinks in the room, you can raise your hand, and I guess we'll see what happens on Zoom. Raise your hand if you think that that case study 1 was an experimental study. No one on Zoom's raising their hand, or maybe I just can't see it. Okay, raise your hand if you think that case study 1 was an observational study. I see one thumb up. If case study 1 was an observational. Both of you already answered that you thought it was experimental. Okay, so I think I have 3 people saying experimental. I don't know what everyone else is doing, but maybe I'm not seeing the, yeah. So someone, one of the people on Zoom put their thumb up to mean that number 1 was experimental. And no one's voting for observational, so yes. Oh, I got another person saying number 1's experimental, great. Okay, so what about case study 2? So raise your hand or put it in the chat if you think case study 2 is experimental. And raise your hand or put it in the chat or whatever if you think that case study 2 is observational. Okay, good. There seems to be agreement that case study 2 is observational. So yes, so case study 1 is experimental, right? They're giving people a vaccine or a placebo. Case study 2, they're just looking at data. So it is 2:05. I think that I'm going to, let's take a break now until 2:15. I'm going to set my timer. Okay. So hopefully everyone's back. So we talked about control over the study environment. So let's talk about timing of studies. So again, there are sort of like 2 major bins that we can put these in. They're prospective studies and they're retrospective studies. So prospective study means that you plan the experiment and then you plan the study, and then after you plan the study, you collect the data. Retrospective studies mean that you are doing the study using data that was collected before the study was planned and done. So like you're using existing data, right? And so that existing data can be like survey data that was from a study that was previously done. So the existing data, it can be from an experimental study, or it can be from an observational study, but it's data that was collected before the study was done, right? So survey data, electronic health record data, things like that. And so something to keep in mind so this can be confusing. So number one, experimental studies are always prospective since they require the manipulation of the study environment. But so like you're always planning the study with that manipulation, and then you're collecting the data as a result of that manipulation. The other thing is that is to keep in mind that, and this can be confusing, I get confused about this, that whether it's retrospective or prospective refers to when the data was collected. It doesn't necessarily refer to events. So the example I have here is that if you're doing a study on whether there was a television in someone's childhood home, if you plan the study right now and you send out a survey to 1,000 people and say, was there a television in your childhood home? That's a prospective study, because it could be a 70-year-old, so the television was in their homes, 60 years ago or something like that. But you're collecting the study after you've designed. Sorry, you're collecting the data after you've designed the study and like during the study process. Whereas if you are looking at survey data that was collected 10 years ago, where someone asked, maybe as a part of a survey that had 50 questions, who knows? And one of the questions they asked was there a television in your childhood home? And I'm doing the study today. That's a retrospective study because the data was collected 10 years ago. Does that make sense? Questions about that? Okay. So then another characteristic of studies is that measurement, the timing and or spacing of measurements. So one type of study is a single observation study where you collect data on the sampling units, so the individuals, whether that is sampling units, a person or a house or a cell or a dog. But you're taking a single measurement at a single point in time or a single point in space on each sampling unit, right? So like, for example, we can go back to let's not say like childhood home, but like survey people right now and say, do you have a television in your home? And then that's the study. I'm just surveying people right now and asking if they have television in their home. So other ways that a study can do measurements in time or space are longitudinal studies. So that means that I'm making repeated measurements over time of the same variable, right? So that could be that like I have a study population or a study population that I'm interested in, maybe like even a sample of 100 people in Durham. And today I ask them, do you have a television in your home? And then in a year, I ask them again, do you have a television in your home? And 2 years, I ask them, do do you have a television in your home? In 3 years, I asked them, do you have a television in your home? So that's longitudinal, right? I'm asking the same question over a period of time of the same study units. And then you can also have multiple measurements over space, right? So it can be that I'm looking at sampling units in different geographical areas, or like these days, you know, a really popular area of research is spatial transcriptomics. So you can look at like over the space of a tumor sample or something like that, right? Multiple observations or making observations in different locations, right? And that could be at the same time, or it can, in which case it would be spatial but not longitudinal, or it could be longitudinally and spatial, right? And then this is then the last is again like pretty specific to research studies. Is the question of blinding, and so usually studies are classified as single blind, double blind, triple blind, or unblinded. And this is only, I can't think of any exceptions, only relevant to experimental studies. So single blind usually means that the study participants don't know what study group they're in. So assuming there's like a treatment and control, right? So we use, well, actually I won't use that. So like, you know, maybe you're giving some drug to, having some people take aspirin to see if it cures their headache, and you have other people taking placebo, right? And they, the participants don't know whether they're getting aspirin or placebo. A double-blind study is where neither the participants nor the people who are directly interacting with them as part of the study, so doctors or nurses, neither of those groups of people know the study group assignments. So the participants don't know whether they're getting an aspirin or placebo, and the doctors and nurses that are interacting with them don't know whether they're giving the subjects aspirin or placebo. Then triple blind is though like a double blind, but also the people analyzing the data don't know the group assignments. And then an unblinded study is a study where everyone knows, like the participant, the people interacting with the participants, and the people analyzing the data don't know what, everyone knows what the group assignments are, right? So the participants know that they're getting an aspirin, or they know that they're getting placebo. A couple of caveats on this. One is that these aren't the only variations, right? You can have a study that's unblinded for the participants and the people interacting with them, but the people analyzing the data can be blinded. And you could, in theory, have, I think it's really uncommon, but I'm not going to say it never happens. You can, in theory, have like a single blind study where the participants know what they're getting, but the doctors and nurses don't know. Anyone have, I guess first, anyone have questions about this? And so why, any thoughts about why you would bother to say, have an unblinded study or a single blinded study or a double blind study or triple blinded study? Why are there these different options? What's the point?
To reduce possibility by creating errors which is interpreted or how it's from administrative in general.
Yeah, so yes, to avoid bias. So how could there be bias if in the different situations? Well, how could there be bias if it's, I guess, started with unblinded?
Well, an unblinded, for example, you have an experimental design placebo or something like that. The whole concept of placebo won't actually function for people that know that what they're getting is medication, and it might also influence the decisions they make. For example, if with the administration of the vaccine, they know that they were administering a vaccine that was potentially effective, so that would have any effect that might impact their actions.
Yeah, so that's a good, so I actually want to, I think you said something that I'm going to disagree with, which is that if they know that they're getting a placebo, then the placebo might not be effective. I'm going to disagree with you there because, well, I don't know, maybe, so if they know that they're getting a placebo, the drug could be effective whether they know they're getting the drug or getting a placebo, right? The issue that often people are concerned about, I think maybe you're saying this in part, is placebo effect, where someone thinks because they're getting, even if they're getting placebo, if they think that it's real, then they can see an effect of it, right? So, and this is well studied. There's lots of research showing that there is a placebo effect, that like if you give someone a placebo and you tell them it's real drug, people will actually see some benefit. But yes, I think so. Excellent. There's an excellent point about the vaccine, that if you give someone a vaccine and you tell them you gave them the vaccine, and you told the people who you gave placebo that you gave them placebo, the people who got the vaccine might behave differently. Like they might go out and be like, oh, I'm going to go visit my friend who has whatever, COVID, flu, whatever it is, that they might engage in risky behavior that they wouldn't otherwise, right? So I got my COVID vaccine. I'm in a COVID vaccine study. I'm going to go out. Now I know that I got the COVID vaccine, so now I feel comfortable going to visit my mom or my friend who has COVID, right? Whereas the person who got the placebo was like, oh, I got the placebo, it's not going to help me. I'm not going to interact with anyone, right? And so you can get, the goal is to have everyone in the study. You don't want the intervention affecting how people behave, unless specifically the goal of the intervention is to affect how people behave. Like, for example, if you give them some sort of training or education, right? So so that's fine, that's single blinding. So why would you need to do double blinding?
We don't want the healthcare professionals to treat patients based on the intervention outcomes, right? And they might
Oh, actually, can you use the microphone? I keep on forgetting. I forget to do it too.
Okay. So double blinding is basically because you would not want the healthcare professionals that are providing service to kind of be biased towards participants based on their intervention arm.
Yeah. So for one thing, they might behave differently, yeah, right? Another thing is that they might, if some of the measurements that you're doing are subjective, like how healthy does the person, I mean, it's going to be less subjective than how healthy does the person look, but there are some characteristics that are subjective according to the doctor or the nurses, right? If they know the outcome, if they know who's getting which treatment, they could be biased in their reporting. And what about triple blinding? Why do you need the data analysis people? Thanks.
The different like statistical tests that people analyzing the data, the like perspectives they might implement, or the hypotheses they might have about it, could all be influenced by like their subconscious desire to see a specific outcome based on the group assignments, particularly if they have like stake in the publication or just in the outcomes of the study in general.
Yeah, and there can also be cases where like sometimes there's like the data analysis is done, like let's say you're one of the outcomes is, say, looking at an X-ray and seeing how well a bone healed, or seeing whether a tumor got smaller, or seeing whether a tumor got larger. And it's something that there might be some subjectivity, or like looking at like a biopsy sample or something like that. There might be some subjectivity in there. And so if the people reviewing that are blinded, then that helps. Okay, so then why would you do something unblinded? If there seem to be all these good reasons for it, it seems like you should really do things triple blind, right? Why do things double blind, single blind, or unblinded? Anyone on Zoom have a thought?
Maybe if both intervention and control groups are having different maybe intervention, like it's not intervention versus placebo, but intervention versus another type of drug. Yes.
So that, yeah. Any other thoughts? Okay, so someone on Zoom says not ethical. Yeah, so like, for example, it could be that I'm actually trying to think of an example. Oh, actually, two people said it might not be ethical. It might be unblinded for ethical reasons. So like one example can be like, for example, if the intervention is a surgery, so it might be, you might say, well, it's going to be, how do you blind that? So one way to blind it is actually to give sham surgeries. That's been done. But you might decide, well, that's actually too risky to do that. But it turns out that there are studies where people have their clinical intervention surgeries that people have been doing for 20, 30, 40, 50 years, and they do it because everyone knows that it works for like improving, I don't know, knee pain or whatever. And so there's some cases where people have done studies, double-blind studies, or I guess single-blind studies of surgeries that everyone knows works. And it turns out when they do the surgery, when they've done the study, it turns out the surgery group comes out worse than the people who got the sham surgery, right? So there can be lots of reasons, right? It can be more expensive or more complicated to do things blinded. It can be that it's just like really difficult or impossible blind, right? So like, for example, if you're giving someone a drug and like there's a known sort of common reaction to the drug or something like that, the people who are getting a placebo aren't going to have that reaction. Okay, so case study one, I have like a little snippet at the bottom there of case study one. So easy question is case study one, single blind, double blind, triple blind, or unblinded?
Double blind.
And how do you know?
It says it.
Yep, good. That's why it's an easy question. Okay. So, oh, wait. That's me. Yeah, okay. Maybe let's take 3 minutes to, so read the question, read the like text at the top. And then there are 3 questions at the bottom, numbered 1, 2, and 3. So take like 3 minutes and try and answer those questions, then we can discuss afterwards. Oops, wrong thing, sorry. Okay, are people ready? You want a little bit more time? Anyone want a little bit more time? Does that mean everyone's ready? Okay, I can take that as yes. Okay, so anyone want to say what the research question is of the study?
Is there an association between the amount of time since a participant's last routine physical and their perceived trust in healthcare providers?
Okay, let's see what I have. Oh, wrong thing. Why is it there? Oops. That's all the answers. Sorry. Okay, and what about the number 2? What is the primary outcome of the study? Yeah, go ahead.
Perceived trust as measured by survey.
Okay, and is the Duke study, is it prospective or retrospective? I hear retrospective. Anyone want to vote for prospective? Okay, why retrospective? Yeah, exactly. Yeah. So so the primary, yeah. So it the research question that I have is there an association between perceived trust and time since last physical? The primary outcome is time since last routine physical, and then yes, it's retrospective. Questions or thoughts about that?
Yeah, I also thought the outcome was trust in healthcare providers.
So it's a good question. So I think the outcome that they're measuring is let me think about this. I got to think about that. Well, oh, okay. So I think that the way this is phrased, I think I'm going to stick with that answer. I want to think about it because I'm going to give you that this is a little bit tricky, but I'm going to defend that answer. So I think the way this is phrased, it says whether there's an association between the amount of time since a participant's last routine physical and the perceived trust in healthcare providers. I think that the assumption is that the perceived trust in healthcare providers is going to influence whether, yeah. This should be reworded because it is, because it says association and it could go either way.
Yes, no, that makes sense.
It's a good point. I'm going to actually make a note about that.
So it could be either one, right?
I think it could be either one. I think that in actuality, the way the study was done was.
I think that's one of the challenges of cross-sectional study. Like you don't know which one is actually the predictor and which one is the outcome.
Yes. Okay. Sorry. Okay. Maybe let's come back to this if there's time. I can make myself a note. Don't look at that. Okay. So let's talk about data types and summary statistics. And again, this is like pretty basic, and probably a lot of people are familiar with this, but I think it is helpful, even if you are familiar. I mean, some people maybe aren't, and this is your first time thinking about it. But it is helpful to think about the data carefully, because I can't tell you the number of times that I've encountered data where there's problems, and if you thought about what or like their incorrect conclusions, and if people had kind of spent a little bit of time thinking carefully about like the data and whether it actually made sense, then it could have been avoided. Whenever you're collecting data, it's a good idea to do some what's called exploratory data analysis, to kind of look at the data and see whether it makes sense. This can and really should be done with a combination of summary statistics and data visualization. And it should involve people with domain knowledge. So it should involve, if the people analyzing the data don't necessarily know what's an expected range for these values, or are there sort of specially significant values that need to be treated differently. So sometimes that might require domain knowledge. I know, like, for example, I go to the doctor's office and, draw my blood and do blood tests, and you look at the results, and or even like blood pressure, right? I get my blood pressure measured, and like, I don't really know what normal range is. And so if you don't know what normal range is, then you can, you don't know what the results mean. And if there's a value that's like 1,000 times the normal range, like, is that even possible? So, like, for example, 2 examples here. So sometimes missing responses are given like a special coded number. So it can be like a 999 or a negative 999 or a -1 for a value that like should only be positive, or a 0 for a value that can't be 0. Or another example here is a systolic blood pressure reading of 350 millimeters of mercury possible. I'm guessing no, I actually don't know whether that's possible or not. But it's important to know like what the normal range is and what the possible ranges are, and whether there are special values that are reported for missing data, or data where it's out of the the range of sensitivity of the instrument. So first we'll talk about like numerical representations of the data. And here's where we're going to actually like do a little bit of using R, although like I said, I'm not going to be doing it hands-on too much. And so often people will want to represent data, summarize it by looking at measures of the central location and the spread. And of course, you need to know like what measures are appropriate for different types of data. And then for, like I said, it's useful also to use graphical representations. And so, so plotting the data and knowing like what's an appropriate way to plot different types of data. So, let's talk about what different types of data are, and then I think maybe once we're done talking about different data types, we'll take a break. So one major bin of data is categorical data. So categorical data, it's, as the name implies, it's categories, right? And so categorical data can be binary data where there's only one of two values that are possible, right? So it can be a yes or a no, it can be a 0 or a 1. So like two examples of that is like a hepatitis C virus test result. And so now it could be that there's underlying that test, there's some sort of quantitative value, but the way it's reported by a pathologist or in a chart is often going to be, is it reactive or non-reactive, or like this would be another way of saying that is the test positive or is the test negative? Another type of binary value could be, is the person on Zoom or are they here in person, right? And so that's not a yes or no question. That's, you know, the answers are possible Zoom or in person, but it's still binary. You can think of that as a binary value. So another type of categorical data is nominal. So this is going to be where you have more than two possible values. You could use nominal for two possible values, but there's some benefits of classifying that as binary data. And this is where there's some sort of group assignment or some sort of group category, but there's no natural ordering for that. So for example, if you're doing a study where people are randomized to one of three arms, so it could be 3 different treatments, or it could be placebo and 2 different treatments, then the randomization arm, you can call that, you know, arm 1, arm 2, arm 3, or you could call it, you know, placebo, drug A, and drug B. There's no specific ordering. We'll get to ordinal in a second, where there's categorical values where there's some sort of ordering. Or it could be like classes of HIV drugs, right? So, so protease inhibitors or NRTI, I don't remember, but different classes of HIV drugs, right? So those are categories. There's no specific order to them. So ordinal values are when you have categories for which there is a natural ordering. So one thing that you're going to encounter probably at the end of today, but you've probably encountered before, is what are called Likert scales, where you can say that you strongly agree, you agree, you're neutral, you disagree, or you strongly disagree. And so there is an ordering to that, right? It doesn't, you could sort of flip it so it's strongly agree as first and strongly disagree as first and strongly agree as last. But I think that we can all agree that agree should probably be between neutral and strongly agree, and disagree should be on the other side of neutral, and strongly disagree should be farther from neutral than disagree, right? So there is that ordering there, right? even though it's categories. Another sort of categorical data is when you have numerical data that's not necessarily categorical, but you're sort of binning the data for whatever reason, either sort of simplicity of analysis or for statistical reasons. So like you could have, relevant to, I guess, case study 2, HIV copy number, where one group would be copy numbers less than 10,000. Another category would be copy numbers between 10,000 and 100,000, and another category would be copy numbers greater than 100,000, right? So that's numerical data, but you're categorizing it. So I have a note here just to keep in mind that sometimes categorical data is assigned a number. So like sometimes yes can be 1 and no can be 0, or as we already mentioned, like -999 could be no answer. Those numbers are just sort of like placeholders. They're often there for like either statistical or data storage purposes. I don't know if you noticed, but that was those sort of numbers were used in the data dictionary that we saw. But you have to keep in mind that those numbers don't have inherent, they're not really numerical, right? They're just representations. Questions about categorical data? Actually, if you have questions, hold on a second, and I'll talk about quantitative data, and then we'll take a break. So data that isn't categorical is quantitative data. So these are like actual values that are measurements of usually something physical, right? And there's 2 major groups. There are discrete quantitative data. So these discrete quantitative data, you can usually think of it as countable things, where it's not like you can't have a fraction of something. So like, for example, it's integers, it's not a decimal number. And so like, for example, a discrete quantitative value could be how many times did the patient visit the ER last year, right? You can't have like 3/5 of a visit to the ER. I mean, it's like you like put 1 foot in the ER, but then you leave, right? It's either you visited the ER or not, or like how many children does the subject have? Do they have 5 children? That you don't have like thirds of children, right? So those are discrete numbers, and like I said, the way that I think about this is, can I like actually look at things and count them, right? So like, for example, I'm looking at the classroom here. If you're not here, maybe you can't see it, but they're chairs, right? And so if someone asks, well, how many chairs are there in the room? A reasonable answer probably wouldn't be, 20 and 2/3, right? What does 2/3 of a chair mean? I mean, I guess it means that like the chair is like kind of broken, but that's not what they're asking. Like nobody is asking like what about a 2/3 of a chair. They want to know like how many people can sit in a room. Continuous quantitative values they're real numbers, right? So it's not necessarily countable. So these can be things like height or blood pressure. And you might say to me, so in some ways it's uncountable because it's continuous values. So like, for example, if I have values like 2.1 and 2.2, you might say like, okay, well, 2.1, 2.2, those are like kind of countable. But there are an infinite number of numbers between 2.1 and 2.2. And I can prove this to you because if you give me a number and you say, or if you try to enumerate all the numbers between 2.1 and 2.2, I can just add another digit to the right. 2.10, 2.11, 2.100, 2.101, I can always add another digit to the right. And so there are an infinite number of numbers. If it's something that's not countable, if it's something that's continuous, there are an infinite number of numbers, you can't count it, right? So you might say to me, height, well, that's like, I'm 5'7". You're not actually 5'7". You're 5'7" within the limits of how you've been measured, but you're 5 foot 7 point something inches, right? And the same with blood pressure, right? Your blood pressure, maybe, you get told it's, I don't know, 80/60. I don't even know what real blood pressure numbers are, but really that's the number of significance that are reported, but it's a continuous value. I will say as a caveat to this, I have at the bottom, that for any measurement, there's a limit to the accuracy. So like, for example, age might be reported in whole numbers, right? If you ask a kid, like, how old are they? Well, if you ask an adult how old they are, they'll say, I'm 33. If you ask a kid how old they are, they'll say, well, I'm, 5 3/4. Actually, it depends on how old the kid is, how many significant digits they give you, right? But technically, a person's age is measurable in fractions of a second, or in milliseconds, or in picoseconds. We usually don't measure it that way, but it is measurable to like infinitely, in theory, infinitely number of significant digits. And just like, for the height or the blood pressure, right? It's reported as a certain number. If you're measuring someone's height, the ruler only has a certain fineness of measurement, but it's still a continuous measure. Questions about that before we take a break? Okay, so I see 3:05 now. Let's aim for 3:15. Hopefully, yes. I'm not hearing anyone saying no, so I'll take that as yes. Okay, so we're talking about quantitative data. So categorical data, binary, nominal, ordinal. Quantitative data, discrete and continuous. So remember the data dictionary that we looked at a while ago? So take a minute. I should have actually said this before, but take a minute and look at the different the different values that you see here, and think about whether you think it's a categorical, or and if so, what type, or if it's numerical data, and if so, what type. Okay, anyone need more time? Okay, so participant identifier. Actually, don't know what I would call that. Let's skip participant identifier. Well, it's yeah, it could be numeric. I wouldn't necessarily think of it as ordinal. I would say numeric discrete. Yeah, so it could be numeric discrete. I mean, the identifiers don't necessarily need to be numeric, right? It could be like a license plate sort of thing, right? Sometimes they are in order that the participant was enrolled. Some of them are, there are several here that I think are tricky and we could call different ways. So medication adherence, not non-adherent status. Categorical. Anyone disagree? SID, someone says SID would be a nominal, even if the values are numbers, I think. Yeah, so I think that it could be, yeah, I mean, I think nominal sounds reasonable. Okay, so medication adherence, not adherence, you said was?
Nominal.
Yeah, anyone else? So we have a nominal for medication adherence, non-adherence. I'd actually think of that possibly as a binary. I mean, you could not, you know, like nominal of, yeah, I mean, you could, anyway. So gender.
So?
Yeah, so it's going to be categorical for sure, right? So, and often traditionally it's binary male female, but actually I think in this study we'll see if we have time. It's actually it is nominal. I think it's one of these two studies. I think it's case study number 2. Okay, so time from baseline. Yeah, so it is continuous numerical, although it's probably represented, it says in parentheses here, years, it's probably represented in the data as an integer, but it is technically a continuous variable. So age at enrollment. Yeah, I think it's going to be the same. CD4 cell count, cells, which is given as cells per millimeter, cubic millimeter.
Numeric continuous.
The numeric continuous. So I'm going to argue here that this is actually discrete numeric because it's a count. Although the way it's measured, actually the way that it's measured, I think is by flow cytometry. So I think it actually is a count. I have seen, you know, you might treat it as continuous. And I guess you could say, like, depending on how many cells you actually count, you might be doing a division there, right? Because or like how big the sample size is. But I'm going to argue that you could consider it as discrete. Okay, what about HIV RNA copies per mil? Yeah, it's probably the same, although technically the way that it's measured is not, you're not directly measuring individual copies. So the value, so it is sort of a count, but the mechanism by which it's measured is actually often a continuous number. These are, some of these values are messy, right? It's never quite as simple, or it's often not quite as simple. Okay. What about weight? Yeah, it's numeric continuous, although it's probably, it says here kilograms, it's probably represented as an integer, but technically it's going to be continuous. HIV medication class combination. Yeah, so it's probably going to be a nominal categorical, and we kind of saw that before. I used that as an example. VL bound, I don't even know what to, I think that that's actually like telling the limits for something, so we'll skip that. And then death. Yeah, so it's probably yeah, someone's either dead or alive, right? unless you're in Monty Python skit. But yeah, so that's going to be a binary categorical. Okay, cool. I think it's useful to like say, because it's more complicated than. Yeah. Okay, so so now let's actually start thinking about like statistics, like summary measures of statistics. And so we'll start off talking about numeric summaries. And so this is numerical summaries is any situation where you have a large collection of data and you're trying to summarize it by like one number or maybe a few small numbers. So we can think about what's called a central tendency, and people are probably more familiar with the specific central tendencies like mean and median than like the term central tendency. And you can also have measures of spread, which again, people are probably more familiar with the specific measures of spread like variance, standard deviation, and interquartile range. And you can also have things like minimum values, maximum values, percentages, things like that. So we'll see most of these. So just a quick look. This is one case where I'm actually showing you the code. This is, we've loaded in the case one data. And here, if you have a data frame that you've loaded in and you run the summary function of it on it, the base R function, it'll try and summarize the data in a way that's meaningful. And we can look at some information here. Where's my cursor there? Right. So like, for example, here, treatment is one of the variables. And so that is, this is case study one. So this is the vaccine, right? So this is, I assume actually, oh no, wait, I don't know what that is. This is treatment. This is whether they got the placebo or the vaccine. But you can see other things here that it's hard to know exactly, and we'd have to go back and look at the data dictionary, and some of these things there are lots of different things. But like, for example, treatment here, you can see the minimum is 0, the maximum is 1, the median is 1, the mean is 0.5004. So anyone have any thoughts about that? Like what does that mean? A little tricky. Huh? Yeah, what's the, why do, like this is treatment. I don't know what this is, but this is treatment. And the numbers seem kind of funny, right? The minimum is 0, maximum is 1. The mean is 0.5004. The median is 1. The 25th percentile is 0. The 75th percentile is 1.
I mean, if you had a ton of zeros and ones, and you just had slightly more ones than zeros.
Yep. So thoughts about like why this variable looks like that?
I'm assuming it's like a binary variable that's being treated as a numeric.
Yes. Yeah. So so treatment is placebo or vaccine, right? So this is, so I think placebo is 0 and vaccine is 1. Yeah. And so it doesn't make I want you to look at this and think about it a little bit, just because it doesn't make sense to actually summarize it with median or mean, right? Because, and we'll talk a little bit about that more later if we have time, because it's a categorical variable. And so, and this is what I meant to actually show you. So we can get R to make like a slightly prettier version of this, but it's the same data. Here's with case number 2, and here's the slightly prettier version. So these values are, I guess, a little bit simpler. So this is again, the like adherence to treatment. Gender is giving us, again, it's R is deciding to give us like summary values that are not very meaningful, because we know this must be categorical. And I think that, well, so we can see things like weight and age that do seem to have like sort of more meaningful, these are meaningful summary values. Okay, so let's get a little bit more specific. We're gonna have like a toy example here. Well, first, actually, let's say, we're gonna use a little bit of describe how we're gonna represent information. So for several examples, we're gonna represent the sample size by n. And then specific values within the sample will represent either by X or Y, and we can have like a Y with subscripts. So let's do we're gonna generate a very simple data set. We're gonna suppose that we sampled 5 individuals with HIV from some population, and we measured their CD4 count. So the number of CD4 positive T cells that they have per milliliter of blood. And so N is going to be equal to 5. So we have a sample size of 5 individuals. And then here are the values, right? Here's the value for CD4 count for individual 1 is 194. For individual 2, it's 87. For individual 3, it's 385. For individual 4, it's 241. And for individual 5, it's 37. I'll just give you the answer really quick because we're running really short on time. So how do we represent this in R? We can make a vector with these values, and we can assign it to some variable CD4. Okay, and we're going to use that later. So here we can do the same thing with our case study 1 and case study 2 data. We can get the N by looking at the number of rows. And so for case study 1, we have 2,504 rows to that's the population size. And then we can just pull out, here we're going to look at the age values from just a few subjects. We can look at the first 5 values. This isn't in any order, it's just in order that they're entered in the data table, right? So for the first 5 subjects, their ages are 35, 42, 49, 25, 34, and 38. And then we can look at the last 5 also. Sorry, 6, not 5. So first 6 subjects in the data table and the last 6 subjects in the data table. Okay, so that's just like a very simple way to represent information. So we can also represent the data as order statistics, which means that we put some sort of, we've ordered the data in some sort of way, usually from smallest to largest or the other way around. And so we represent, before, remember, we were representing things as Y sub 1, Y sub 2, Y sub n. For an order statistic, you put the index number in parentheses to indicate that it's an order statistic, not just the data, the sort of random order of the data. So Y sub 1 in parentheses, if you look at this, now it's sorted in order from smallest to largest. And if we wanted to do this in R with that vector that we made before, that CD4 vector that we made before, we can just call the sort function. Okay, and then we can also pull the data, the age data from the case 1, and put this in order. So there are actually several different ways to do this. This is a sort of tidy verse sort of way to do it, using, I guess, all dplyr functions, where we're sorting the data frame by age. We're going to filter out any entries where there's no age information, and then we can, here we're looking at the first, second, third, and last entries. And so we're using slice to pull out the first, second, third, and last entry, and then using pull to take that column and make it into a vector. Any questions? All right, and we can do the same thing for case 2. Here we're looking at the log 10 viral load. So that's the log 10 value of the RNA copies per ml of blood. And also this is an order statistic for that, right? So it's sorted. Okay, so that's very simple. We can now be like slightly more complicated and talk about measures of location. So something that I'm sure everyone's familiar with is the arithmetic mean, right? You just sum up all the values and divide by the total number of them. You know, this is a simple way of saying that is a expanded representation. I see I forgot to delete something there. And then for our CD4 sample, this is taking those numbers, adding them up to get 944, dividing by 5. And so the mean value for CD4 count across our toy example is 188.8. And then we can also do that with the mean function in R. And if we want to do that for our data frame, we're going to do similar to what we did before, use pull to get the age column, pull it out as a vector, and then we're going to use the mean function here. We need to say NA.RM equals true. That'll drop any values that are NAs because there are some NAs in our data set. Usually you're going to have some NAs in real data. And often this is what you want to do, but you shouldn't do it blindly. So our mean age is 31.4. And similar for case 2, for the log 10 viral load. Actually, here I'm using a slightly different way of doing it. I'm using doing the more tidyverse way of doing it, using the summarize function. Okay, so median is, again, probably people are familiar with this, is another measure of the central tendency. And so it's the simple way of, one way of thinking about it is you have an order statistic. So you sort all the numbers in order and you take the middle number, right? And so here for our toy CD4 example, where we had 5 values, you can, this is the order statistic. So we can just look at the 5 values. We can just look at the third one. That's the middle value is 194, right? So what do you do if you have an even number of, if n is even? So if n is even, then so like if we drop the largest value, then if n is even, then you take the two central values, right? So in this case, we have 1, 2, 3, 4. So we're going to take the 87 and the 194, and we're going to take the mean of them. So then our median for this this smaller sample of 4 values is going to be 140.5. Questions? Okay. I assume that people are all familiar with this. And again, this is to calculate the median age for case 1. Similar, we're going to do poll and run that through median. And again, we need to remove the NAs. And if we want to do that for the log 10 viral load in case 2, then very similar.
So poll is pulling that variable?
So poll is a dplyr function. Yeah, and so it basically, so dplyr is usually, this is a data frame, right? So poll actually takes out a column and it returns that column as a vector. Whereas like other things, like if we did select, for example, even if we just select a single column, it's going to return a data frame. I think that we might be able to get away with, I can't remember if median would work right on it or not, but it's safer to, it's definitely safer to use poll. Some things it'll like, if you give it a data frame with a single column, it'll like work okay. But it's safer to use poll. And actually we could do, I'm not doing this, but we could use, for everything I've done so far, I showed you for mean, I use summarize, so we could use summarize here too. It'd be like a more tidyverse way. Okay, so I just showed you mean and median. Those aren't the other measures of central tendency, but they're the most common ones. And what sort of measure you use, it depends on the type of data. So for continuous data, whether you use mean or median or something else, it really depends on the shape of the distribution. For categorical data, like we saw, it often doesn't make sense to use mean or median. And so there are other measures of central tendency that make sense. Sometimes it makes sense to use the mode. Sometimes it doesn't make any sense to use measure of central tendency, central location for categorical data. And then, so let's look at, for continuous data, let's look at a couple examples to show you like when mean makes sense and when it doesn't, and when median makes sense. So here's a symmetric, or actually several different symmetric distributions. This is a t distribution, normal. Actually looks kind of funny normal, but I think this is normal, and this is a beta distribution. And all of them are symmetric, right? So the sort of, if you look, you can kind of identify the center, and they're symmetric around the center. And so in this case, in all 3 of these cases, when there's a symmetric distribution, usually the mean and the median are going to be about the same, and you can use either one. For a normal distribution, like often the mean is a good representation. But there are lots of different asymmetric distributions. So here's a chi-square distribution or an exponential that both of them are skewed left. I'd say skewed right. Skewed, they're right, they're positively skewed, right? And so you can see, like, here's the probability distribution, here's a histogram representation, box plots. And so you can see that they don't look normal. And so it's, we might not want to be using the mean. Just here's another negatively skewed distribution. And just to show you 2 different, like a right skewed and a left skewed distribution. And this is the red is the mean, the blue here is the median, and then this is the mode. Mode is the like most common value. And so you can see that there's like, you know, a significant difference between the, not specific, but there's a difference between the mean, the median, and the mode. And in this case, mean is probably not the value that we want to use to represent the central location of this distribution. Questions about that before I keep going? So we can talk really quick about measures of spread. So again, this is probably something that people are used to. Sample variance, basically like how spread out the data is. So we can calculate that by calculating the mean of the data, and then for each value in the data, subtracting the mean from it, squaring that, and then summing up those numbers and dividing by the total number of values minus 1. And so this is how we, this is expanding that, and this is how we'd calculate that for our CD4 sample. Remember that the mean was 188.8. And these are the individual values. So we're subtracting 180.8 from 194 and squaring that. Subtracting 188 from 87, squaring that. And then we divide by 4 because there are 5 values. If we want to do that with our real data, we can again use poll and use the var function and calculate our variances. Another measure of spread is the standard deviation. So that's the square root of the variance. And so in R, that's really easy to do, is SD for our CD4 vector. For our case studies, again, we're going to use poll to get the variable, that column as a vector, and then run it through, use the SD function, and we're going to remove NA values. Another way to represent spread is the interquartile range, which is basically, again, we're gonna use the order statistics. I'm gonna stop in a second because I'm contractually obligated to make sure that everyone does the survey. So use the order statistics. The median is the 50th percentile value. So it's the middle value, but you can choose whatever quartile, whatever percentile value you want. And so the interquartile range is the 25th, is the difference between the 25th percentile value and the 75th percentile value. So here, I'm showing you for our N of 5 CD4 count values, how we can calculate the 25th and 75th percentiles. So it's 87 and 241. And then the interquartile range is just subtracting, like I said, subtracting the 25th percentile from the 75th percentile value. We can also just directly calculate that using the IQR function. So it's 154. And again, we can, similar mechanism to calculate both of those for our real data, pull them and use the quantile function or the IQR function if you want to. Quantile function to get those quantiles, or the IQR function to actually get the interquartile range. And then again, just like for mean and median, they're different. For different data sets, we're gonna choose what measure of spread we want to use depending on the data. So variance and standard deviation are reasonable when you have normally distributed data, but if there are a lot of outliers or the data skewed, then they can be misleading. And whereas the interquartile range is pretty robust to outliers. So it's similar to the median in that sense. And then quickly, I mentioned this before, I'll just touch on it now. So we can also have other sorts of summaries. So like, for example, with categorical data, I mentioned that like it didn't necessarily make sense to always look at the categorical data by look at categorical data as like a mean or a median, but we can do things like look at proportions. So if we want to break out in the case study one by treatment by gender, right? So we can look at the different gender classifications and ask, what percentage of people who identify as female got placebo versus vaccine? What about for people who identify as male? What about people who identify as transgender female and transgender male or other? Okay, it is 3:55, and I didn't make it through graphical summaries. But like I said, I am obligated to make sure, or at least extremely strongly encourage you all to do the survey. Uh-oh, that's not showing. Maybe if I go, no, okay, it's gotta, come on. So I think I've said this before, but I'll say it again. So first of all, if you didn't sign up before, then here's the sign up. Hopefully Lauren is on still in Zoom, and she can drop the links in Zoom. If you didn't sign up before, please sign in before, please sign in. And please take, I'm stopping now with 4 minutes left. So you have 4 minutes to do the survey at the end. And we use this information, number one, to show the National Institutes of Health that we're using their money well by training you, but also, and possibly even more importantly, we use this information to make changes for next year and even possibly make changes for, maybe not next week, but like future sessions. So, and actually, I don't know if 2 QR codes on the same page are problematic, so I did that on purpose. I thought, if anyone hasn't signed in and they need the other QR code or the other link, please let me know. And I'll actually really quick try and join the Zoom, and I can drop. I can find the link.
I just added the link, Josh.
Oh, thank you.
Yeah, so we really appreciate if everyone can fill it out.
And I'm happy to entertain questions if people have them. I know that was a little bit whirlwind, and as I feared, didn't cover everything that I planned to. I think go a lot slower than the people who normally teach this.
Josh, how many people are in person?
2.
Okay. I think that
I mean 47. It's totally packed in here. Thank you. Thanks for coming.